Hello, in this video I'm going to show you how to set up a discrete time stochastic system example based on the Pol Oscillator using our tool PRoTECT. The first thing is the system description we want to set to discrete time and stochastic. Then we can set the dimensions of our system using dim, and we can set the maximum degree of the barrier certificate we're trying to find using max b degree. We use the max b degree value in two different ways depending on whether parallelization is checked from the right-hand side checkbox. If parallelization is checked, we use the max b degree to select the maximum degree of the barrier, and we select all even values below and including this and run them in parallel. We collect all of the results together and then return to the output the barrier with the highest confidence. If the b degree is selected and the parallelization is not checked, then we will simply run one simulation using that degree value. The L degree value is an optional term for the Lagrangian degree, and this by default is set to the same value as the dimensions. PRoTECT offers two types of solvers, MOSEC and CVXOpt. When we describe the state space, the initial state, and the avoid region, we describe the lower bound and upper bound of these regions, separating each dimension by a comma. When we have multiple avoid regions, then we will select the Add Avoid Region button on the left-hand side, and we can also delete an avoid region if we accidentally create too many. In this example, we have two different avoid regions, which are then going to be added like I'm showing here. We describe the dynamics using a SymPy expression, which uses asterisks for multiplication and double asterisks for exponents or powers. It's important to use the correct SymPy variables, starting with x1, x2 for the dynamic variables, and var sigma 1, var sigma 2 for the noise variables. These will be used to calculate the moments of the equation, which is very important in the barrier, and so they should not be omitted. If the user wishes, they can define the level set values lambda and gamma and the constant c. If the user wants to optimize and find the highest confidence, then it is essential to also provide the lambda value, and this is a required parameter in that setting. For these discrete time stochastic systems, we enable three types of noise. Normal noise with a mean and standard deviation, which should be separated by a comma. An exponential noise with a rate, which again, each rate per dimension should be separated by a comma. And then lastly, we also provide a uniform distribution with upper bound and lower bound values separated by a comma. In this Pol Oscillator, we're going to consider uniform noise with bounds, lower bounds minus 0.02 and upper bounds 0.02. The time horizon is a required parameter which we use to calculate the confidence and is multiplied by c. You can also set the minimum confidence of the barrier you're trying to find if you wish, although it may be that there is no solution for that confidence level. When we click the button Find Barrier, it will then try and find a solution that we're looking for, and it will return this inside the boxes barrier, the confidence will be returned in the confidence, and the different level sets will be returned in those respective level sets and c-value. I'll now demonstrate an example where we're optimizing and we've set the lambda value to be 1000. When I click Find Barrier, you can see that we find a barrier function with a confidence of 0.885, which is quite high. This barrier can then be used for plotting the graphs, and this barrier certificate has guarantees. I look forward to seeing you in the next video.